In this video, we're going to look at the energy associated with the formation of ionic bonds. In the past, you've probably been told that ionic bonds are strong bonds, but you haven't been told why they're strong bonds and what it means to be a strong bond. So we need to start at the beginning. It has everything to do with electrostatic attraction and repulsion. You see this all the time, especially in the winter. You get shocked. Lightning. When you take a balloon and you rub it on your hair and then you stick it to the wall. This is electrostatic attraction. In this case, you've had a buildup of positives in your body because the carpet is taking up the electrons, and the electrons in this metal see this and they are attracted to it, so they zap on over. Same thing happens in lightning storms. As the clouds push past each other, they have a buildup of negatives. Well, here's the ground. Ooh, ground looks pretty attractive because it has all these positives. So you get lightning, the traveling of the electrons. So they're attracted and they are pulled towards each other. Remember, a force is a push or a pull. So this electrostatic attraction or repulsion is actually a force. Let's look a little bit more closely. Electrostatic attraction and repulsion is the force of attraction or repulsion between two electrically charged objects. You're electrically charged if you are a proton, an electron, the nucleus, remember the nucleus is positive, an ion, a polyatomic ion. Anything that's positive and negative, or two positives or two negatives, experiences this electrostatic attraction or repulsion. Please do not confuse this with magnetic attraction, which is different. So recall that attraction is when a negative and a positive are attracted to each other. They have a force between them that pulls them together. If there's two positives or two negatives, the force pushes them apart. Let's apply this to ionic bonding. So first you have that electron lost. Remember, this has low ionization energy and this has a high electronegativity. After that occurs, the entire sodium is a plus and the entire chloride is a minus. So they are attracted to each other. Therefore, they come closer. It's this closeness that I want to examine. Before we move too far with forces, I want to talk about potential energy. Specifically, we're going to get to the electrostatic, but let's get a good understanding about what potential energy is and the way we know it. So if you look at the picture, the girl has the ball somewhere above the ground. You know that that ball has potential energy. Because gravity is going to pull it down, we call that gravitational potential energy. You've probably never heard it referred to as gravitational, but that's what it is. When she drops the ball, that gravitational potential energy is transferred into kinetic energy until it finally gets to the ground. Right as it hits the ground, it's all kinetic energy. And then when the ground hits it back and it comes to rest, there's no gravitational and no kinetic energy. Well, the question is, where did it go? You can't just lose it. And the answer is in the creation of sound, heat, deforming the ball or the ground. So the gravitational potential energy was transferred in the very, very end all into making the sound and we'll call it sound energy. It's just making those waves and mechanical waves, so it's another mechanical energy, or into somehow messing with the ball and getting it all deformed, or putting a crater in the ground. So energy was conserved because gravitational became a different form of energy in the end. We have something similar going on when we have ions apart. When we have the plus and the minus apart, and they're attracted to each other just like the ball was attracted to the ground, it has the potential. We call that electrostatic potential energy, and I abbreviated EPE. As they come together, the amount of electrostatic potential energy decreases. And then finally, they're as close as they're going to get. So it lost a great deal of electrostatic potential energy. Where did it go? The answer is all of that electrostatic potential energy was transferred into thermal energy. And just like it sounds, it has everything to do with temperature. It released all of this energy into thermal energy and raised the temperature of the area surrounding this interaction. So this means that the formation of ionic bonds has the transfer of electrostatic potential energy into thermal energy that is causing the temperature to rise around it. And when this happens, we say that it is exothermic. The thermal energy is gotten out of this interaction. So let's take a quick step back and really look at the energetics of ionic bond formation. The first involves the exchange of electrons. So if we had Na as our X in the first bullet, and it required energy to pull off that electron and make the Na plus, it would require 496 kilojoules of energy per mole of Na. So this process, because it requires energy going in to make it happen, we call this endothermic. Notice the number is a positive number. In the formation of the Cl minus, we have the Cl, we add an electron to it to form Cl minus. Energy is released from this process, and we put a negative there because it's released, and that's exothermic as well. So the exchange of electrons requires energy, and then we get down to the formation of the crystal lattices. First, remember we have this EPE here, electrostatic potential energy, and when it comes together, it releases thermal energy because that potential has to go somewhere, and then it forms NaCls that look kind of like this. Oh, but then you have another source of electrostatic potential energy. So more thermal energy is released when these come together. And if you multiply that by a lot, you get the crystal lattice formed. So there's a lot of electrostatic potential energy that is being transformed into thermal energy. So it's not just about forming the NaCl, it's about forming NaCls in a nice pattern in a very structured crystal lattice. Let's quickly recap. When you are creating an ionic bond, there's energy involved in exchanging those electrons. Some of it's endothermic, some of it's exothermic. Now, when you have the ions, they're attracted to each other. They have electrostatic potential energy until they're together. All that electrostatic potential energy, when they're together, is transformed into thermal, or almost all. Then NaCl's are attracted to other NaCl's because they're electrically charged. So all of that electrostatic potential energy is transformed into thermal energy. And then we multiply that by billions. And we get the formation of crystal lattices and the energy involved in that formation. So, lattice energy. It is the amount of energy released as thermal energy when crystal lattices are formed. So remember, you've got the EPE between the positives and the negatives coming together, being transferred into thermal, and then you have that where you have something already together attracted. So a lot of energy is released as thermal energy as these crystal lattices are formed. The more energy released, the stronger the bond. So the question becomes, okay, well, how do I know what's going to release more energy? And there are two criteria. Bonds are strongest, and I probably should say here ionic bonds. Well, I'll try one more time. Ionic bonds are strongest when the ions are smaller. That's why we studied ionic radius. And the charges are larger. So let's look at these two, sodium fluoride and magnesium oxide. The sodium plus is the gray in the middle. The fluoride is the F minus on the outer ring, or in the green. In this one, magnesium is pretty small, and oxygen is just a little bigger than the fluoride. Notice the magnesium is smaller than the sodium and has a higher charge. So I predict the magnesium oxide is going to release the most energy, which makes it the strongest bond. Let's look over here. If you look on this table, you see magnesium oxide is 3,795 kilojoules of energy per mole. So for 1 mole of magnesium oxide to form, 3,795 kilojoules is released. Sodium chloride, for the same amount, 1 mole, is 788. So I was right. The small magnesium and the greater charge, the magnesium and the oxygen, releases more energy. There was more electrostatic potential energy between them because they were a higher charge and smaller. Therefore, more energy was released when they finally got together.